Well, I'm going to talk sort of a much broader, which is sort of what is the ecological resiliency of Alberta's wetlands. And this is sort of a summary of about the last 10 years of work that I've done. I spent 20 years working on peatlands, and then the last 10 years or so working more on marshes and other types of wetlands. And some of my students I put down as co-authors as well. But the questions that I really wanted to address is, do wetlands in Alberta show resilience to disturbance? Specifically, I'm going to look at peatlands and very briefly, and then shallow open water wetlands as affected by agriculture. And then secondly, can restored or created wetlands achieve the same structure and composition as undisturbed natural wetlands, which is really, to me, can they achieve resilience? And I'm going to look in that regard at permanent marshes in both the white zone just outside of Edmonton, but still boreal, and in the oil sands. And then conclude with a little bit about some of the future marshes in the oil sands region. So first thing, when I was asked to give this talk, I said, what is resilience? I had to go and look it up, and even after some exploration, it's actually, as Clive has pointed out, it's very difficult to know exactly what do we mean by resilience. And there are broad and relatively narrow definitions. But the broad definition is the capacity of a system to absorb disturbance and reorganize while undergoing change, so as to still retain essentially the same function, structure, and feedback, and therefore identity. And that is the capacity to change in order to maintain the same identity. So that's sort of a broader definition. But the narrower one, which is actually used in aquatic and wetland systems, is defined as the amount of disturbance that a system can absorb without a change in structure and composition. And I should point out that really when they're talking about structure, it's the species composition of the populations, the communities, but it's also the functional attributes of them as well. So it's not just what we think of as structure. So in my view, in looking at and studying all these different wetlands in Alberta for these decades, is resilience of wetlands actually depends on how you define the term resilience. It depends upon the wetland class and how we define the wetland functions. And obviously it depends on the type, severity, and frequency of disturbance. Do we have large drastic changes, small frequent changes? And individual wetlands, are we looking at the resilience of an individual wetland for, say, certification? Or are we looking at for the resilience of the wetlands as part of a larger landscape? And then the time lags, recovery time since disturbance. And wetlands are often thought to be very resilient. But in fact, I think that they vary greatly in terms of their resilience. And that depends upon, I'm sure most of you are well aware of the 5 main classes of wetlands in Alberta, or in Canada: the bog and fen, which are peatlands, and the shallow open water, swamp, and marsh. But in fact, what we really find when we're looking at wetlands, but whether they're mineral-based or peatland-based, is that there's a lot of movement and transition. So changes in the structure, changes in the functional attributes, and they can evolve and change over time, depending upon the hydrology, the substrate, and things like that. So while we have five classes, we have actually many transitional types of peatlands as well. So in terms of peatland disturbance in the boreal zone, there's a whole entire suite of types of disturbance. Some of them, of course, completely knock out the wetland or the peatland, and others may have varying effects over varying lengths of time. But one of the things that, to me, at least I feel, is the resilience to disturbance, and that means then, do peatlands maintain similar substrate, water, and biota? In other words, it's the substrate, the water, and the biota that actually define what a wetland or a peatland is. And particularly important in all of our peatlands is the ability to lay down peat. That's an essential attribute of a peatland, and that they're dominated by mosses, which are the primary producer, which actually produces peat. So in my view, if we're building a peatland, it has to have those two attributes. But it's still questionable. For example, this is a wooded fen up in northern Alberta. and Dave Lockey, one of my students, found over 350 species of plants that are just in a very relatively small area. Is that absolutely essential for a peatland? But when you're coming to some kinds of disturbance, is peat mining, which takes off the top bog peat and leaves all of the fen peat, and then they start a very good reclamation process on top of that. Would you call that a resilience to disturbance? Partly that depends upon the time frame, and that also depends upon whether you want to define this as a permanent loss. It can come back to some kind of peatland over time, but whether you would call it is definitely the loss of a bog, but it is can retain a viable, healthy fen. And Alberta government is coming up with some kind of definition of what a permanent loss is, and I'm not sure it's exactly clear how they're going to assess peat mining in the future. In my view, given the fact that it's so easy to lose organic matter to decomposition, peatlands really are not a very resilient ecosystem to try to reclaim on the landscape, mainly because of this inability to rapidly build peat-forming complexes. So, and I haven't given some of the measures that we could use, but I certainly could do so if I thought about it. Anyhow, I'm going to talk about more now about how have I been measuring resilience in terms of primarily open water wetlands and various types of marshes. And we measure them in terms of the structure, the composition, and the condition of the biota, the substrate, and the water. And in other words, everything that defines the wetland. And we've been trying to establish a threshold whereby the system changes state from one state to another. In other words, if it changes state, do you call that a different state, a different regime, or is that part and parcel of what one may have just in normal dynamics of a wetland system? So the first sort of case study that I'm going to give is, I wanted to know whether the amount of agriculture in the buffer zone, happens to be a Boreal, of a shallow open water wetland or a lake, does it change ecosystem state? Does it change regimes? And so what we've found, and this has just been recently published, is absolutely, if you have agriculture and it's close, a lot of it in the buffer zone, you do increase the amount of nutrients that are coming into the wetland, both for nitrogen and for phosphorus. But do you actually change the regime or the alternative state? And so, for example, up here, if I can find this, what we have in very low nutrient situations is we have two alternative states, one dominated primarily by algae or one dominated by submersed aquatic vegetation. If it's really low nutrients, they have low density or productivity of both. In Alberta, though, where we have naturally high nutrient phosphorus, especially in the soils, we actually can have two alternative states. One with relatively high biomass of algae and low submersed aquatic vegetation, or alternatively, low biomass of algae and high submersed aquatic vegetation. And of course, we see this all over the world, these alternative states. And there's a whole literature on alternative states in shallow lake literature. If you have a lot of nutrients coming in, you basically have really turbid, eutrophic lake and very little submersed aquatic vegetation. And so what we have then, primarily in Alberta, is this clear state, which is dominated by submersed aquatic vegetation, a whole suite of submersed aquatic species, lower chlorophyll, lower phosphorus, shallower depth, and all the zooplankton, or those that eat algae. Or in the contrast, the other alternative state is the turbid state, very little submersed aquatic vegetation species or density, a lot of different algal species, high chlorophyll biomass and productivity, high phosphorus, etc. And the algae are not a different suite of zooplankton that does not control the algal growth. So those are the alternative states. And some work that we published several years ago, we can see an actual threshold between 18 and 20 micrograms per liter of chlorophyll that defines the difference between these two states. Completely different plants and animals on both sides of this threshold here. But Did agriculture cause an increase in the turbid state? And actually what we found was it did not lead to an increase in algal concentrations. So despite the fact that we had a lot of agriculture, it didn't change our ecosystem state. And what we actually find is, in this picture here of an agricultural region, you have a clear lake, a turbid lake, a clear lake, a turbid lake. And what we actually are finding is that, and this is up north of Uticuma, definitely a boreal, completely undisturbed area where there's no agriculture whatsoever, over a 9-year period, whatever number year that is, over 40–50% of these lakes switched from a clear to a turbid state and back again. And in some cases, they switched 4 times in this time period. Are our shallow water, open water wetlands, are they resilient to increases in phosphorus? This comes back to this definition of resilient. No, they're not resilient if the definition means that they maintain. They're not resilient if that means that you maintain the similar suite of species and productivity, either algal or SAB dominated, across that range of conditions. But then they are resilient if you consider it as sort of the ecosystem as a whole, and what we find in both agricultural and natural areas of Alberta, because they switch back and forth from one regime to another as conditions change. So I don't know if you call them resilient or not. That depends on the definition. So it really depends upon the time frame of the definition and our social goal. So next I'm going to talk about another example we did is, are our created or restored wetlands resilient? And this is very important because we have wetland legislation that says we're supposed to compensate for wetland losses. And so are we compensating by putting out healthy wetlands that adapt to changing conditions, or are we not? And so how do we actually measure this? And the way we measured it is actually using what we call the reference condition approach, which uses natural, minimally disturbed sites to explain the natural variability of the biota. And then we compare that constructed or disturbed sites with these natural sites. And I think that's going to be absolutely key in the oil sands region as well. And so if then, given that we use this reference condition approach, then if the created or restored wetlands achieve what we call the same scores that we're at, the way we measure resilience, as the natural sites, then I would say that they actually are resilient. And the scores that we're actually doing, how we actually measure it, are looking at a physical chemical disturbance gradient, in other words, all the environmental parameters, which we call stress gradient. We look at the plant community, and we look at various other animal communities, wetland-dependent songbirds, and others. So it's really critical, if we're saying they have to achieve the same type of scores that we use in this case as the natural sites, and then we'll say that they in fact are resilient. And so we did this here just east in the Boreal transition zone and Boreal mixed wood just east of Edmonton, and we're trying to answer the question, are constructed wetlands, which are replacing some of the ones that were destroyed, in the same condition as the reference wetlands. And looked at reference agricultural, restored wetlands out in the agricultural area, and then 2 types of stormwater ponds. So the first question that we're trying to answer is, do constructed wetlands have the same environmental stress as our reference sites? What are the environmental conditions they're subject to? And we actually had 80 wetlands that we looked at, and we looked at about 48 environmental parameters, and using a principal components analysis, looked at how they fell out across a gradient of all of these 48 different parameters, environmental parameters, all mostly physical and chemical parameters. It turns out that only 8 environmental variables are really important to distinguish this entire range of constructed, restored, and natural wetlands. Those that relate to water, those that relate to sediment, and those that relate to the physical morphology of the wetland. And so we can form what we call a stress gradient, where on one hand we have all the 80 wetlands down here, and then form a single score by adding them all together, these 8 parameters. And what we find is that our stormwater ponds, whether they're naturalized stormwater ponds or even restored wetlands, tend to have much higher stress. And the natural range of variability for the natural wetlands is right down here and have much lower stress. And we looked at, in a number of different studies, 6 main biological indicators, or indicator assemblages: open water, emergent vegetation, higher up on the marsh, the wet meadow vegetation, macroinvertebrates, waterfowl, and wetland-dependent songbirds. And we found that all of these biological communities actually responded to about 8 environmental parameters. So that means then if you're a consultant and you really want to look at wetlands, you don't have to go out and measure the 48 parameters that we actually measured. Really, you should at least make sure that you measure those, because all of the communities actually responded to those environmental variables. And some of the field-based tools that we actually have is, so if all 6 environmental bioindicators are sensitive to the same environmental variables, can we use the biota to evaluate wetland health? And we did this using plant-based index of biotic integrity, which we call an IBI. And we did some bird-based, and we did some other ones as well that I won't show. But what we did is, looking at several hundred attributes of the plant community, the marsh community, we found that actually 4 main sort of what we call metrics were the most important metrics and related most closely to these environmental parameters. They have to be responsive to the change in environmental conditions, not just be changing because they're being grazed or disease or something else. And when we put all these together, we can make an IBI, or Index of Biotic Integrity score, for these wetlands. And when we then plot that, we plot the stress score. This is very high stress, low stress, a high IBI score, and a low IBI score. What we actually find is that the constructed wetlands have relatively poor condition. The restored ones are slightly better. And based on that, I would say that these are not a very resilient ecosystem and actually are not very good in terms of their compensation. So then we want to move on to the oil sands area, where I've been working up there for about 10 years on various kinds of wetlands. And again, to answer this question, can created oil sands wetlands achieve the same abiotic and biotic characteristics as natural wetlands? And again, we're using the reference condition approach. We're looking at shallow open water marshes, and they have a characteristic salinity, water depth, vegetative community. We look, among other things, at the submersed aquatic vegetation and the marsh community. Now I want to emphasize that we had 38 reference sites. We looked at all of the sites on Syncrude and Suncor that were over 7 years old. So we looked at every single wetland that had formed on the mine sites. But I want to point out that these were not constructed to be viable wetlands. These just kind of formed, or they were built for some other purpose. And I think there's a serious inadequacy up there because we actually don't have anything to test in the oil sands of good marsh community, which I think is the best option for the future of wetlands in the oil sands. So the scores that we get, to me, primarily reflect the fact that we haven't really tried to build good marshes up there. So what we did find, though, is that oil sands area, it's going to be much higher salinity than, say, what most peatlands can tolerate. But in our study, this is total dissolved solids. Our reference sites formed this entire range that, did that as did the sites on the oil sands, either those that were physically disturbed or those that had tailings contamination. And again, we looked at the environmental conditions. In this case, we looked at 52 environmental variables and did a principal components analysis to see what separated the entire range of wetlands, and found that 8 parameters were the most important parameters. Those, some that related to water, some that related to sediment, some that related to the physical characteristics, and some that related to contamination of the oil sands. And we line these all up, and they are significantly different. The reference are significantly different from the physically disturbed, which is different from the tailings contaminated, with these much less healthy wetlands at that end of the gradient. And so we just have about 10 papers on showing how to establish these kinds of relationships, but in fact, what we're trying now is to say, how can we make this available for people to use and to monitor? Because it's pretty complex to develop these assessment tools, but once you have them and you look at them in the appropriate system, it's actually pretty easy. So luckily, Alberta Innovates and Osram have funded us to actually develop a handbook and a website, which I think is actually on Osram's website, for a video. And we're showing how to actually measure and use a stress gradient. So measure what you really do. If you want to go into a new wetland up in that area, you measure these 8 parameters. Then you get a stress score. You put that stress score into the gradient that we actually have, and you have a number. So you know what is the environmental stress of that particular area. And so that gives you a score of where it might be in terms of its environmental conditions. We're doing the same thing in terms of its biological communities. And so this is an example of whereby we are looking at the submersed aquatic vegetation community, and if the biological community or the attributes of that biological community has a very good response, a response to the stress gradient, you include that in as part of your index of biotic integrity. If it's, for example, diversity had a terrible relationship to stress gradient, but percent alkali tolerant submersed aquatics had a very good relationship, 1 positive, 1 negative. So out of 60 different metrics that we looked at, 11 of them were related to the stress scores, and we put them all together, and we can find then that we have a submersed aquatic vegetation index of biotic integrity against the stress score, and a very reasonably good linear relationship whereby we can establish thresholds, which we did actually statistically, where you have a good submersed aquatic vegetation community. If your score is over 160, then it's good. If it's less than 160, it tends to be bad. So notice we have 2 of the tailings contaminated sites that actually they probably just happened to form in the appropriate place that are in a relatively good biotic condition. They still have actually very high stress scores in terms of the physical chemical conditions, but biologically they're good. And we can have a similar threshold in terms of the environmental conditions. Less than 12 is healthy, greater than 12 is unhealthy. We did the same thing for the wet meadow community, and just to remind people, not only are we looking at the vegetation, we're also looking at something like biomass or annual production, vegetation, zone width, relative diversity of exotic species, relative diversity of halophytes. So these are, out of several hundreds and hundreds of metrics that we looked at, these turned out to be the most important, and from them we could then make a similar wet meadow marsh index of biotic integrity to assess the health of that. So reference sites, again, are healthy and have a high IBI score, and the constructed ones are generally not very healthy, except for those few which I think we ought to look at in more detail. Why are they actually healthy? And in fact, what we really need to is to design better wetlands that are going to be able to tolerate the range of salinities that we're going to be having in the oil sands. So this technique is also useful in terms, if we want to monitor over time, we could actually say monitor 1 year, 5 years, 10 years, and we can basically decide whether both the environmental conditions improve or the biological conditions improve, and actually use that for some kind of compliance monitoring if we so choose. So anyhow, we're going to be having a handbook coming out on this hopefully in a couple of months. So the question we have then is, can we achieve resiliency in constructed oil sands wetlands? And I actually think that these are Boreal transition zone marshes of many different types, wide range. I think that we can achieve resiliency in our wetland landscapes on the oil sands if we try to look at a range of designs of different types of wetlands and don't just get fixated on one type, one class of wetlands. And we have to construct our wetland landscapes to include a diversity of wetland types with a range of salinities, a range of water depths, and an adaptation to a change in climate. So we not only want the wetlands, we want the landscape that they're in. And so there would be, looking up on Syncrude, they have huge flat level sand tops. They could have a large number of these types of small wetlands up there as long as they put in some kind of clay layer or a material layer that would keep the water that comes in the spring from flowing out. And so if we're actually looking at the size distribution of all this sort of whole suite of wetlands, we find that most wetlands are actually very tiny. This happens to be for an area just east of Edmonton. And very few wetlands actually on the landscape are large. It seems to me right now what we're planning is wetlands that are 3 to 20 hectares in size. We need to be thinking about wetland landscapes that include a whole suite of much smaller wetlands. Another thing that I was actually surprised by is that, I thought, well, if I put on what we call temporary wetlands that only have water, say, for a month, or seasonal wetlands that might have it for 2 or 3 months, and semi-permanent wetlands, when global warming comes along, these wetlands will disappear. Well, it turns out, it actually, based on some modeling that's been done by Johnson et al., the temporary and seasonal wetlands do survive in a much drier and warmer climate. They did these modeling based on 2 and 4 degrees centigrade of climate warming. So we can have wetlands on the landscape as long as we keep the water from flowing out of the bottom of these wetlands and design it properly so as to accommodate, this changing climate that we are going to be having in the Fort McMurray over the next coming decades. And so I think that with proper design and proper experimentation, we should be able to build viable, resilient wetlands. Thank you.